two sets of lecture notes on clustering. And there's also two sets of lecture notes now about phase. There's an introduction to phase, and then there's an on-premise phase. And, when we get to the phase stuff, a lot of that we're going to skip. So a lot of that is background because you've already done it in either 701 or 705. In fact, the plan is this. So today I'd like to go and finish the clustering material. Then Wednesday's class, we're going to start the Bayesian material. We're going to start with a lecture on foundations. What I mean by that is foundations of inference, because it's my experience that there's a lot of confusion about what the differences between Bayesian and non-Bayesian inference is. And so I'm sure you all know the mechanics of you take the likelihood and you multiply it by the prior and the posterior. But what does it actually mean? How is it actually different from the stuff we've been doing so far? So what I'm going to talk about on Wednesday is some strange examples that you've probably not seen before that show you that Bayesian and non-Bayesian methods can lead to vastly different answers. And then you want to try to understand what does it mean for them to come up with different answers, all right? So this is going to blow you away. This is going to be like, you may not sleep again after Wednesday's lecture, all right? This is going to be a mind-altering experience. So that'll be on Wednesday, hopefully, depending on how things go today. Then we'll go into stuff like non-parametric phase and get back to just doing the mechanics of it. But I think it really is important to talk about kind of the philosophical foundations, because otherwise I find there's just a lot of murkiness and confusion about what's going on. All right, so let's finish the clustering. We've done, now there's many, many, many types of clustering, right? And we did density clustering first. The Bayes stuff we'll talk about later when we get to the non-parametric Bayes. So we have to decide what else to cover. And I think probably the main one is k-means, where we'll look a little bit, you've looked at k-means before, but we'll do a bit of theory today. And again, this one we don't want to get to until we've done our mind-altering lecture on Wednesday. Which maybe I'm going to like explode your brains so much on Wednesday that you may not even want to see this. So we'll have to see what that is. And if you do need therapy after Wednesday's lecture, CMU will cover the cost. So I guess, but before we go to k-means, I want to do mixtures. I think we can do mixtures quickly because you did this in 701, right? I'm talking about using a mixture of Gaussians. You did this in 701, correct? No? You didn't? EM algorithm? Yes? You didn't apply it to mixture of normals? I thought you did. Well, because what I wanted to concentrate on again was not the mechanics of doing mixtures of normals, which you already know, but maybe I'll need to review it, but to show you that there's a lot of unexpected things about mixtures of normals. In some sense, what I really want to do when I cover k-means and mixture clustering is to let you know that you're actually in very dangerous territory. There's a lot of weird stuff going on here that you might not be aware of. I have this preference for density clustering, as I said, because it's clear what you're estimating and what you're doing and so on. Whereas these things, I think, again, there's a lot of unexpected behavior that you might not be aware of. So I thought I'd quickly do mixtures. Let me make sure my assumption that you already know it is correct first. So the mixtures actually is at the end of the first set of notes in clustering. This is page 10. So what I mean by clustering by using mixtures of normals, so let me tell you exactly what I mean, and then you can reassure me that you already know how to do this, is that I'll draw it in one dimension, but this would happen in general in D dimension, is you would fit a density which is now parametric, so it would be a mixture of Gaussians that would look like this. You would say P of X, these are mixing weights, and this is a Gaussian density with some mean vector uj incident j. And so we pretend the data come from this finite mixture model, the number of components will be a parameter, let's say k. And the hope is that this is it's a parametric model, but the hope is that it's flexible enough that it's a pretty good approximation of whatever we're doing. And then once we have an estimate of this distribution, it's pretty easy to do the clustering, because this is like saying that every observation came from one of these components, and we just have to guess which one. So did you talk about how to estimate the parameters in this model? Is that everyone? Well, either you did and you don't want to tell me, or you did and it went so fast you didn't get it, and you remember it, or you've forgotten it, or you didn't cover it. I don't know how to separate those four hypotheses. So I'd assume that would be okay. Let me just remind you then. Let's pretend it's the first time we've seen this model. How would I estimate the mu's, the sigmas, and the pi's, which are the parameters of this parametric model? What method do we use? What do we estimate parameters? Model. Maximum. So if we call all of these parameters, and there's a lot of parameters here. There's the pi's, there's the mu's, there's these sigmas, which are matrices. Let's just call them all the parameters effectively psi. Then we simply take the likelihood function, and then we maximize it to get the ML. So in principle, we now have an estimate of all the parameters, right? Actually maximizing that MLE is a little bit painful because this is a product, but within each product is a sum. But I think he did. Now, does this ring a bell? What algorithm do you use to try to find out at least the local maximum over like that? EM? I need to feel more secure that you actually did the EM algorithm. How many people think that you did the EM algorithm in 701? That's weird. All right. Well, I hadn't prepared to talk about it because I assumed you'd do it. So maybe we'll do this in a future class. For now, let me just say, I'm going to remind you quickly what it is, and we can go back and do it in more detail if necessary. It's just a method of trying to find a maximum of this likelihood function. The likelihood is a horrendous mess. It's got many maxima. But at least you try to find the local maximum. The EM algorithm, so just to remind you, it looks like this. Well, there's two steps in the EM algorithm, the E step and the M step, the expectation step and the maximization step. And what one does is you can create this latent variable. It will look like this, say. For each observation, you can create this latent variable, which is all zeros and a single one, which is saying this observation I came from component 2 of the mixture, or component 1, whatever. If you knew Z, this hidden label, it would be really easy to do this because you could now say, oh, these observations came from component 1, component 2. You can just do separate analyses, each one just be normal like that. And what the EM algorithm does is it just iterates between guessing Z and then given the Z's, maximizing the likelihood. When you put the Z's in, the likelihood becomes very simple. We can write, in fact, P of X really as P of X given Z, summed over all possible configurations of Z. Sorry. Yeah, that's right. But if you knew the complete likelihood, meaning if you didn't have to sum over the Z's, if you knew the Z's, again, it would be an easy maximization. So basically what the EM algorithm does is it takes the log likelihood, it takes the expected value of the log likelihood, where the expected value is over the randomness of the Z's, and you get something easy to maximize. And you alternate between taking that expected value and maximizer. So if you have forgotten that, or you didn't actually do it, we should probably cover that in this class at some point, so we'll come back to that point. We'll need to do some probing and find out a little bit more about how much you covered there. For the purposes of this lecture, let's assume you believe me that we have an algorithm called the EM algorithm for maximizing this likelihood. And so once I have the maximum, clustering is pretty easy because by Bayes' theorem, I can ask myself, for each observation, what's the probability it came from group 1 or group 2 or group 3? What is the probability that xi is from cluster J? Well, that's the probability. So again, you can think of this as you're drawing a cluster number, let me call it Gj, with probability. So the probability that your cluster assignment is J is pi j, and then x, given that your cluster assignment is J, is just from a normal. That's another way to write out this model. Somebody draws a label for you. You're from one of the clusters. J equals 1 to k with probability pi 1, pi 2, up to pi k. And given your cluster assignment, you're just drawing from that model. That's another way to write the model. And now by Bayes' theorem, once I tell you all the parameters of the model, the probability you're from cluster J is just the probability of being, what's the probability you're in a cluster? Let me write it this way. Let me write it more clearly. Given your x is what's the probability of x given you from cluster J. I'm just going to switch it around with Bayes' theorem. And that's just pi j times, I'll call this phi j. And then the sum of those. And remember, there's all kinds of parameters in here, but we can stick in the MLE. So this is the standard way of doing mixtures of normals clustering. Let me review the whole thing again. We assume that the density is a mixture of a finite number of normals. There's some parameters. You estimate them by maximum likelihood. Once you have those parameter estimates, for each observation, I now can say, what's the probability this guy came from cluster 1, cluster 2, cluster 3. And you can either now do what's called soft assignment, which is for each person, I don't say which cluster you're in, but I just say there's a certain probability of you coming from each cluster. Or I can pick the highest probability and assign you to a cluster. So that's mixtures of normals clustering, which has some advantages because there's a clear model for the clustering. What does it mean to come from a cluster? Well, it means you're from one of these 10 normals, and I'm telling you which one you came from. And again, I was kind of assuming you'd done that in 701. Now, it's just what I really wanted to emphasize was that there's problems with mixtures of normals clustering. It's very hard. Mixtures are interesting models because they're kind of intuitively very simple, right? A mixture of k normals seems like a very simple. And yet, it turns out that both computationally and mathematically, they're extremely complex objects. In some sense, you don't even know what the distribution of the MLE is, for example. Okay, so there's a lot of stuff that people kind of sweep under the rug. So what I really want to do is kind of warn you about these things. And so this is the bottom of page 10 now. Well, the first one is, statisticians always say, once we have the model, it's really easy to do that maximum likelihood. We even have an algorithm for it called the M algorithm. But that's actually kind of a fiction. Finding the MLE is NP hard. In fact, there's many local maxima, and you really want to find the global maximum. Nobody knows how to do that. It's an impossible problem. What you usually do is run the EM algorithm a few times from random starts, find a local maximum, cross your fingers, and hope that's good enough. That's sort of what really happens in practice. There has been some work actually in machine learning about trying to do things other than maximum likelihood to estimate the parameters that have guaranteed polynomial time algorithms for getting estimates of the parameters. And there's some interesting theoretical results, but I haven't seen anything yet that I would consider practically convincing. If you try to find a function in R or at MATLAB to do it, I don't think you'll find it. So I don't think it's great for prime time yet. But there's other weird things I want you to know about mixtures. And by the way, I'm not trying to tell you not to use mixtures. I just want you to be aware that if you're going to use mixtures for clustering, you should be aware that there's these weird things, okay? So the second weird thing is that the likelihood, the maximum, what is the maximum of a likelihood function? It's infinity. Let me explain that. So, if I have some data, and I have some normals, I can take one of the components of the mixture and put it on top of an observation and let sigma go to 0. And what happens to the likelihood function? It goes to infinity. So technically, the maximum of the likelihood is infinity. The way people get around that is notice that this corresponds to letting sigma go to 0. So if I drew it just in terms of, let's say, sigma, and this is 0, what this is saying is that the likelihood could be going to infinity near 0, but there might still be well-behaved maxima in the interior. So what people often do is either they put some sort of regularization to prevent sigma from going to 0, or if you find sigma going to 0, you restart it or something like that. So when you talk about the maximum of likelihood, you mean the maximum of the interior. Because near the boundary, the likelihood could be infinite. And that can show up when you're actually running the end algorithm. So that's kind of a weird thing. It's not critical. Here's another weird fact about mixtures. Let's start with one dimension. If I take a mixture of two normals, even with the same variance, how many modes are there? And that seems like a trick question. It turns out that if they're well separated, you get two modes as you'd expect. If they're close enough, though, if the two means are close enough, it becomes unimodal, even though there's two components. But now comes the weirder part. When you get to higher dimensions, the number of modes is pretty much unrelated to the number of components. You can have a mixture of 10 normals and have fewer than 10 modes, but you can have many more than 10 modes. And in fact, there is no theorem that tells you exactly how many modes there are. There's lots of special constructions people have created now to show you can have way more maxima, way more modes than components. But those are special cases. I don't think there's any general theorem that will tell you how many modes there are. And the behavior is very weird. There's all kinds of papers with weird examples showing you have 3 components, but there's 7 modes and all kinds of stuff. So unlike mode clustering, when you're doing mixtures of normals, you should not think of the modes, the bumps, as being the clusters. The clusters are defined by these underlying normal distributions. And it's very tempting to think of it as, okay, there's just a mode for each one of those, but there could be fewer or more modes than there are clusters. So that's another thing to keep in mind. All right, now comes something a bit deeper, which causes all the problems for the theory, which has to do with identifiability. So usually when we deal with parametric models, we usually assume they're identifiable, which means if I have 2 different values of, question.
Yeah, I want to ask you about what you said about the modes. Does that mean that the mean shift algorithm, for example, would not work if the generating distribution was something like that, a mixture of normals in k dimensions which has more than k modes?
Well, it depends. Would mean shift clustering work? In mean shift clustering, we're defining the clusters between the modes. So whether you would say mean shift clustering is working and the mixtures is failing or vice versa depends on your point of view.
Okay.
But it's definitely true that there isn't a one-to-one mapping between the modes and the clusters. All right, so we usually assume when we deal with parametric models that they're identifiable, which means two different parameter values correspond to two different distributions. Now, mixture models are not identifiable, but there's a sort of harmless non-identifiability and a very dark and dangerous non-identifiability. The harmless one looks like this. If I have a mixture, I did an example here that looks like this, 0.3 times the normal, mean 0, variance 1, plus 0.7 times the normal, mean 2, variance 1. So if I ask you, what's pi 1? Pi 1 is 0.3. And what's mu 1? Mu 1 is 0. But I could just as easily have written it the other way around. And then pi 1 would be 0.7, and mu 1 would be 2. We've just changed the meaning of the parameters. So in other words, this mixture and the one where I've flipped them, that's kind of like reflecting. What would that be, a reflection or something? We're identifying different points in the parameter space, technically. One of them has pi 1 equal to point. So in other words, here's one parameter vector. Here's a second parameter vector, which in Euclidean space are two different points, but they're referring to the same distribution. That's called labeling non-identifiability. That's not a big problem. That causes some computational problems because there's copies of the same distribution in different parts of the space. But for technical stuff, that doesn't matter. We can always agree to pick one of the possible labelings. This relabeling non-identifiability is kind of a nuisance, but it's not a big problem. It's more a matter of definition. The second type of non-identifiability, though, is more serious. And it's sometimes called degeneracy. Actually, I can draw a picture of it now. I don't have a picture here, but I'm going to draw a picture of it. Let's look at the following special mixture. So I'm going to look at pi x mu1. Let's take the variance of mu1. So I'm taking pi times the normal with some mean mu1, and I'll take the variance of mu1. And 1 minus pi times pi x mu2. So this is a very simple mixture. It's only three parameters: pi, mu1, and mu2. I'm going to draw the parameter space here. Can I do it? Well, sort of. Here's mu1. Now, I'm not very good at drawing two dimensions. So I'm going to leave out one of the parameters. Pi here. I'm going to leave off pi 2. But here's the more serious type of non-identifiability. Suppose I tell you pi is 1. So we're dealing with this distribution. What happens? How is the distribution now affected as I change mu2? mu2 has disappeared. So in some sense, when pi is 1, if I had drawn mu2 in here, I would have a whole plane where I'm really referring to the same, no matter where I put mu2, it's the same distribution. There's this whole subspace where the parameters vary and the distribution is not changing. And clearly the same thing happens with pi is 0. Pi is 0. As I change mu1, the distribution isn't changing at all. These are all referring to a single normal distribution. Right? Let's also look at what happens if I took mu1 equal to mu2. That's valid. So here's mu1. What happens to pi here? Doesn't even enter it. In other words, this distribution, for any distribution here, if you think of pi as coming up this way, as I vary along pi, the distribution doesn't change. So these are sometimes called singularities or local non-identifiabilities. There are subspaces in the parameter space where the distribution doesn't change, where there's a whole stretch where the parameters are changing. You change pi, you're changing the parameter space, you're moving in the parameter space, but you're not changing the distribution. These are very weird things. And this pretty much screws up all theory known in statistics. So there's all kinds of things like the MLE we taught you is asymptotically normal, gone. If you did a likelihood ratio test for whether there's, is it a two-component mixture or a one-component mixture? So in 705, when you did a likelihood ratio test for dropping a parameter, you learned that was asymptotically chi-squared. No one knows the distribution. Actually, it's not completely true. People have expressions for it, but they're not something useful that you can make use of. The Fisher information. The Fisher information, you know, you take 1 over the Fisher information, you get the standard error. In these models, the Fisher information is 0 in some places. It's singular. If you try to prove that the optimal rate of convergence, that the MLE is converging at like 1 over root n, you will be shocked because you won't be able to do it. In fact, it's known that for certain mixture models, the rate of convergence is 1 over n to the 1/4, but I don't think in general it's known what the rate of convergence is. So, what to make of all this? Again, I'm not saying, you know, you should not use mixtures. They're obviously useful in lots of situations. But what you sometimes see people doing is they do mixture modeling and then they act as if they can just do the MLE and do a test or do a confidence interval or do whatever they would normally do. And you just have to be very aware that all theory you know no longer applies.
Like, both of the situations you described seem like you should just have fewer mixtures. Like, if you...
Right, if I got rid of that second mixture, I wouldn't have any trouble, right?
Yeah, so if you, as in practice, you like look at it and say, okay, there's probably 2 mixtures, and you make like better statements about the 2.
The problem is this. Suppose I'm trying to decide how many components to put. How do I decide whether I should get rid of that second one? I'm going to have to do a hypothesis test or something. And that begs the very question we're trying to ask. And imagine, and of course, in one dimension we can draw pictures. But now, say you're doing a 10-dimensional mixture. All right, so that's just another warning. There is, I should tell you though, is there a question?
Sorry. Well, what it sounds like you're describing is that you've embedded a model selection problem into your estimation model, something like that. I mean, couldn't you just do the normal things we do from model selection and that?
So like BIC?
Yeah.
We have the same problem. So when we use something like BIC, we use it because there's a theorem that says BIC does nice things. That theorem doesn't apply anymore for mixture models. Now there has been some progress showing that in mixture models, certain good things happen with BIC, but it's still not completely settled. In fact, so I'll tell you, if you're interested in this, we're not going to go off in this direction. There's a very recent body of work that by this, pretty much spearheaded by this Japanese gentleman named Watanabe, I think is his name. He has a whole book on it. Because the same things, by the way, happen in other models too. So lots of latent variable models have this behavior. Neural nets have this behavior. And so he has this whole book all about machine learning and statistics for these singular models. I don't really understand, but I'll just tell you a little bit I understand. The way he looks at it is, he says, look at your parameter space. And here's your set of distributions. And he says the problem is these singularities, that there's whole regions in here where the model's kind of ill-defined and so on, and it might be some sort of weird thing. And then there's this branch of mathematics called algebraic geometry, which is completely devoted to the problem of what they call resolution of singularities, getting rid of these problems. And the main theorem in his book seems to be using some fundamental theorem from algebraic geometry that you can always find a nice manifold. And you can always view your model as having there's a mapping, so it's like there's another parameterization here, let's say U, that maps into here, maps into your model. And that if you just directly use this parameterization, all your problems go away. All kinds of beautiful limit theorems solved. What's unclear to me, and I haven't studied this in any detail though, is how constructive it is. It's one thing to say there exists such a reparameterization. There exists a reparameterization which makes all the problems go away. It's another thing to be able to use that, and so it's unclear to me at this point how well developed it is. There is a guy at Seattle by the name of Matthias Durton who has actually come up with a new version of BIC which tries to use this theory to get a version of BIC, an adjusted version of BIC which works for mixture models. So this is a very new thing. There's not a lot known about it right now. All right. I could go on all day, which would get kind of boring after a while, but I'll just mention one more small point, and then that's enough, because as I said, I really want to make sure your brains are in good shape for Wednesday, right? If I blow your minds today, then Wednesday's going to be wasted. So. But here's one other weird thing. There's a picture on page 13 that when I give you an observation and you say, what's the probability it came from group 1 or group 2, let's pretend I even told you the measure, so there's no estimation to do. Suppose I have one normal like this and one normal like this. No, that's not a good picture. Actually, this picture, I can't do this picture. It's not a good picture because I want to do like this. Well, I'm trying to make the measure look simple. Yeah, so forget the picture there. This is a better picture. I have these two normals. Now, and let's call this, mixture normal 1, mixture normal 2. If I tell you x is here and you had to guess where did it come from, you'd probably guess it came from 1. And if you do Bayes' theorem, you see it has a high probability of coming from 1. And if I have an observation here and say which cluster did it come from, you'd say with high probability it came from 2. But now comes the strange fact. If I go out here, you might end up assigning it to cluster 1. Why? Because if 1 had a slightly larger variance, eventually his tail is going to be above his tail. And so you're going to end up assigning all these observations not to cluster 2, but to cluster 1, which seems very counterintuitive to how we might want to define a cluster. Okay. All right, so what's the point of all this? The point of all this was just to say, if you're going to use mixtures of Gaussians for clustering, proceed with caution. Just be aware that there's these weird things. There's no doubt from practical experience that lots of people find them useful. So despite these problems, they can still be used, but I just wanted you to be aware of them. The most disturbing thing was maybe you didn't learn the algorithm for Gaussian mixtures of Gaussians, which I want to investigate further and come back to that point later. Instead, I want to go on then to talk about k-means and the other methods of clusters. So we're in the second set of notes. We might as well jump straight to page 3. Now, let's try this again. We did do k-means in 701? Yes, thank you. So let's remind ourselves how it works. The nice thing about k-means is that it's simple. The bad thing about it is it may not find very good clusters. So the idea, remember, is I have some data. And let's suppose, for the moment, I've decided I'm going to use 2 clusters. The question of choosing the number of clusters will come back to. So in k-means clustering, what do? We pick some centers, C1 and C2. So maybe I'm going to say here's C1, and here's C2. And then we just take each observation and find the closest center and add up the errors. So we compute, I'm going to call it the clustering risk, Rn, which is the average of xi minus its closest center. And the notation, well, let's do it. The minimum over, sorry, that's wrong. The minimum over the centers of xi. So that would be adding up this, and this. And then, of course, what you try to do is find the centers C1 and C2 that minimize that, right? So that's what you did, is you said we take the minimum in general over vector C1 to CK of Rn. And the resulting centers, so in this case you would expect maybe it would come out like, maybe it's like this, and those are your cluster centers. And probably, I'm guessing they taught you Lloyd's algorithm for doing this, which maybe they didn't call it Lloyd's algorithm, but it's usually called Lloyd's algorithm, which is the iterative. It's very much like K-mean, or like EM. It's an iterative algorithm where what you do is you first put down some starting values. Say starting value C1, C2. Now you take each observation and you assign it to its closest center. So it would look like this one is here. Then you take the mean within each of those groups. That becomes your new C1 and C2. Then you reassign them, take the mean and iterate. So I'm assuming that's the algorithm we thought, right? Yes? Yes, good. Some people call that the K-means algorithm, but I think the right name is actually Lloyd's algorithm, because in principle you could minimize the K-means criteria using other algorithms. So the result is something like on page 4, which is sometimes called a Voronoi diagram or Voronoi tessellation, which is that when you have your cluster centers, what you're doing is, remember, every observation gets assigned to its closest center. That creates these polygonal sectors, which I'm not perhaps drawing great, but anyway, so anything in here gets assigned to this cluster, anything in here gets assigned here. That's pretty bad. Everything here gets assigned here, and so on. That's the Voronoi diagram implied by the K-means clustering algorithm. Okay, so hopefully that's a review. It's simple and pretty intuitive. In fact, you can show that if you take certain limits in mixture of Gaussian's model, take all the variances equal and let them go to 0, you get the K-means algorithm. All right, so good. That's good. There are a few problems, however. So one of them is, like the mixture model, the minimizer of this function. So we're trying to minimize this over C1, C2, CK. Let's pretend it was only one-dimensional minimum. Unfortunately, it's not convex. So there's all kinds of local minima. So one problem is it's not a convex problem and we don't know how to find the minimum. But that problem is, in some sense, been largely solved by something called K-means plus plus, which I'm pretty sure you covered at least briefly in 701, but I'll review that in a minute. But let's first, before we go there, let's just ask a more fundamental question, which is, when do we expect K-means clustering to work well? When do we expect it to return clusters that make sort of intuitive sense to us? Well, when might we not expect it to?
The clusters are well separated?
If they're well separated, it's going to work pretty well. And also, though, there's another thing, which is it tends to work well when the clusters are kind of spherical-ish or something, right? So if I have a cluster that looks like this and a cluster that looks like this and they're well separated, k-means should work pretty well. But if I have a cluster that looks like this, like a ring, and maybe another ring, k-means is not going to be making much sense here. It's probably going to put these together into a cluster and these together into a cluster. This is a case, in fact, where density clustering, the density function will give you nice level sets there. But k-means clustering might not be so good. It's not really a non-parametric kind of a thing. There's even cases where you think it might work well and it doesn't. One of my favorites, which I put on page 6, is actually from Wikipedia, was the first place I saw this. It's called the Mickey Mouse example. So if you look at page 6, and it has to do with imbalance function. So, see, I guess I don't know whether they called them, yeah, they called it the Mickey Mouse example, and you can see why. I guess it's what they do with Mickey Mouse. And so, what ends up happening is, if you run k-means clustering here, it doesn't show up unless you're in color, with k equals to 3. Beautiful. You get one cluster here, one cluster here, one cluster here. It couldn't be better. But when you make them very unbalanced, so when you put small clusters here, you would hope you get 3 clusters like that, but you don't. What you get is this gets clustered together. This sort of gets clustered together, and this is not together. That certainly is not intuitive what we think of as the clusters. Yeah, if I move these far enough away, that problem would go away. So again, if you're well separated enough, that problem will disappear. And there's some other examples you can look at here. But that's not that interesting. The thing I want to focus on, though, is the fixable problem, which is no one knew how to pick starting values. And starting values are really, really important. And up until the last few years, the standard advice was pick some starting values at random, run k-means, and do this a few times. But that actually doesn't work very well. So this is one of my favorite examples of this. Is on page 9. This is what this is 9 normal distributions. And if you just do, and I tell you k is equal to 9, if you take 9 random values to start and run k-means, you'll see you get kind of disastrous results. Why? Well, when are you going to get a good result? You're going to get a good result if you get one value here, one value here, one value here, and if you work out what's the probability if I draw 9 numbers from all these 9 points at random, then I get exactly one in each cluster. It's, it's astronomically small. That doesn't work. So random starting values, even if you did 1,000 times, is just going to be disastrous here. But everything changed in this very simple 2007 paper by Arthur and Vasilevsky, who came up with k-means plus, and it's such a simple, intuitive idea. In fact, I suspect many of us have done this before without realizing you can prove something about it. And the amazing thing is that there's a very nice theoretical guarantee with this. And what this method does is it picks the starting values in a very simple way, and it guarantees that you're going to be very close to the global minimum. Not the global minimum in the sense of necessarily the centers that give you the global minimum, but the risk value will be very close to the global minimum. And here's how it works. So you pick your first center. Here's your data. Okay. And remember, we're still assuming the number of clusters k random and call that a center. So the first thing is just random draw. So maybe you pick x3, let's say. Now we've got our first center. So we put our first center down, maybe it's 3. Second step is we take each data point, we compute the squared distance, and you normalize that. So we take pi is, I'll call it d of xi, squared normalized. Right, so each point I take the distance, I square it, I normalize it, so now it's a probability. You sum up to 1 over all the data points because of the normalization. And now you draw randomly from all the data with these probabilities. Okay, so point close by has a low probability of being selected, point far away has a high probability. So now you have your second one. Now, we have to recompute the weights. For each data point, again, we find the distance to the closest one. We square it, and then normalize it. Now you draw, again, a random point with those weighted probabilities, and you get your third point. And you keep doing that until you get k points. And now those are your starting values for the k means algorithm. So again, people have intuitively been doing things like this for years. You want to pick one point, pick another point kind of far away from that point, and so on. And it turns out what they proved was that so this is a random algorithm. So when I say the expected value here, I mean the expected value over the randomness of the algorithm. And if you compute the risk over the randomness in the algorithm, they showed that that's less than or equal to 8 log k plus 2 times the true minimum. The minimum overall plus points. So this is an example of an NP-hard problem where you can still do something that comes close to minimizing the thing with some sort of guarantee. Now you might wonder though, if k is big, this is not a very good bound. There are things you can do. There are many versions of this now. So you can get rid of the log k. You can replace the log k with a constant. You can just imagine doing it many times, and then with high probability, eventually you can make this constant as small as you want. So there's versions of this improvements that get rid of the log k. There are versions that speed it up. There are streaming versions so that you don't have to keep all the data in memory all the time. You can do it streaming. So now there's been a whole series of papers that have followed up on the basic algorithm. But the cool thing is this is really simple to do. It's very intuitive, and it seems to work. Every time I've tried it, maybe I've been lucky, but this picture is a little bit hard to see on the page, but on the color code, the top right shows k-means with random starting values, which turns out to be disastrous. The bottom left uses another method of describing that, which is sort of okay, but the bottom right is k-means plus plus, and it completely nails the 9 clusters. And obviously there's some chance it'll fail, but it seems to work with very high probability. And the proof of this, by the way, if you look at their paper, you can look it up. It's not very difficult. It's just a simple inductive proof. So that's kind of a big breakthrough. That's, it really, in some sense, solves the problem of choosing starting values and getting those clusters.
What about sensitivity to outliers?
So this gets also to the question of is k-means doing a good thing, right? Because suppose I have clusters like this, and then I have a guy out here. K-means clustering is going to want to call this its own cluster. Is that a good thing or a bad thing? Well, it might be a good thing because it's drawing your attention to this outlier. Or what you might want to do is do something more robust, and there are robust versions of k-means where you replace the squared error loss with something less sensitive to outliers. So robustification is a whole other generalization of k-means. But yeah, you're right. If there are outliers, k-means is going to probably put outliers in their own clusters.
The reason you go for something
So the reason you sample, you create a distribution and sampling instead of say, pick the point that is the furthest off from our clusters, is it also because of
Yeah, so there is a version of that, right? It's called K-centers, where you pick one at random and you find the farthest one, and then you find the farthest one from that, which is sort of a deterministic version. As far as I know, it doesn't have, it's harder to prove a guarantee about it, I think. I might be wrong about that. I think the reason for the randomization was, like a lot of things, it's easier to prove things about randomized algorithms. Okay, any questions? Now, let's go on to talk about the really hard problem of how do you pick K? I'm curious, what did they tell you in 701 about picking K? I couldn't figure that out from the slides. All I had access to was the slides. What did they say to do?
The elbow.
Elbow method, okay, the good old elbow method. All right. So there is no bias variance trade-off, right, for clustering. It's not like prediction where you overfit if you use a training error, but if you use held out data, you would stop yourself from overfitting and you fit the right amount. For clustering, there is no such thing. There is no help. There is no Ys. And you will always get a better and better fit, even at the population level, if you just add more and more clusters. So that's why it's a much harder problem to choose the number of clusters. So what he just mentioned was the probably the most commonly used thing, which is we can compute this loss function. Let me put it back up on the which is just these within sums of squares. We could do this for each k. So we can do it for k equals 1, k equals 2, k equals 3, and plot the risk. It's a decreasing function, so minimizing it's not helpful. But what people often do is this. Let's imagine a test case that looks like this. What's k means going to do when I take k equals to 1? It's going to take the mean, right? And that's going to have a pretty big error. So if I draw this risk, for k equals to 1, it's going to be some big number. When I go to k equals to 2, all of a sudden I get to put a guy here and I put a guy here. There's going to be a big drop in the sum of the squares, so it might look like this. Now what happens when I go to k equals to 3? Well, at that point, I've got a center here, a center here. Where am I going to throw the third one? I don't know, maybe in here. It's not going to reduce the sums of squares very much. There's diminishing returns. So maybe it'll look like this, and it'll go down. So when there are really well-separated clusters, what you typically expect to see, well, I should have drawn one where k was bigger, but you're going to get, I'll draw a better one. So here's one where it might look like this. And there'll be this elbow phenomenon. And so you look for this elbow, and that's telling you how many clusters to pick. Unfortunately, in real life, they rarely look so clear. If they do, it's great, but in many instances, and so I would say the truth is nobody knows how to pick K, and the proof of that is the number of papers that appear every year with new methods for picking K. If we knew how to pick K, it would be solved. And the fact that people keep dreaming up new methods, it's a very hard problem, and I'm not sure that giving you something with provable guarantees will work. So I don't have an answer. I will tell you, though, I want to tell you a little bit something about something that doesn't work, just because it's kind of interesting. Which is, for a while, people were very excited about measures of stability. What if I split the data in half? do k-means clustering twice to see, do I get stable clusterings? Problem is, there's a paper by Ben David and von Luxemburg and Paul that pretty much shows you that measuring the stability of k-means doesn't really tell you anything about how good your clustering is. And I can explain it best with this picture on page 16. Okay? So, what I want you to imagine is if I gave you, I'm going to look at a data set, but imagine we did it twice and we perturbed the data a bit. Would the clustering change much? And if it doesn't, we'll say it's stable, otherwise we'll say it's unstable. So there's some cases where stability is successful. So the top left picture shows you a cluster like this, like this, like this. And if I tried to fit 2k to 2, this would be very unstable. You'd probably get something like, what ends up happening is you get a cluster here and a cluster here. But because of the symmetry, it's equally likely that you'll get this cluster and so on. So this is a success story for clustering. If you repeated this with slightly perturbed data, you'll get completely different clusterings that tell you you should not be using k equals to 2. So that's good. That one seems to work. But here's another one. This is also a success. Is if I try, for this one, if you go like this, and I try to fit too many clusters. So that was I was fitting too. That one was unstable because I was choosing k too small. What if I fit k too big? Suppose you fit 3. You can show that typically what's going to happen is you're going to split that first and then kind of split this. But it's equally likely that you'll split here. And so again, stability will tell you, oh, you made a big mistake by trying to fit 3 clusters together. You're okay. So those are success stories for clustering. Notice the role symmetry is playing here. But now let's look at examples where stability would be very, very misleading. The bottom left picture is very stable. I'm going to put these in here. If I fit k equals to 2, well, the first one is basically dividing it up like this, and then the second thing is going to put a center. So there's going to be a center somewhere up here and a center somewhere down here. And if these two are far enough away from this is very stable. You'll get the same answer every time. And yet, clearly, k equals to 2 is not what you want, right? So here's a case where k equals to 2 is stable, but it's the wrong cluster. And conversely, if I change that other example so it looked like this, you want to do k equals to 2, but if you fit k equals to 3, again, it'll be very stable because you'll fit one here, that's sort of splitting this, but then you'll put one here and here, and because of the imbalance here, it'll just give you the same thing every time. It'll be very stable. So it's going to tell you k equals to 3 is stable, even though there's 2 clusters. So their paper is full of theorems that prove all these things, but these pictures really show you everything that's going on, which is showing you that what's driving stability has to do more with certain symmetries in the distribution than whether you have a good cluster. And I think this really dashed the hopes that these stability-based measures are going to lead to any sort of good method for choosing k. So it's appealing, but when you think it through a little bit more, somehow stability isn't quite measuring what you want. At least not in this form. Maybe somebody will think of it a different way. So somewhat unsatisfyingly, I'm going to leave the question of how to get k kind of open, because I really haven't found a method that I'm really happy with. But there are good theoretical properties of k-means, and I want to review one right now. We could probably prove this right now. One option is to prove it now. Another option is to state the theorem and prove it after we've done VC theory, because it uses VC theory. So you did some VC theory in 701. Do you think you did enough VC theory that we can do the proof, or would you rather wait until we do VC theory in this class and come back to the proof? Does anybody have a strong feeling one way or the other? Well, let's see. Let me tell you the theorem first. The nice thing about it is actually a nice example of how BC theory is useful for proving. So let's ignore the problem of choosing K, and let's ignore computational problems, and let's just say that there's a population quantity and a sample quantity. The sample quantity for any clustering, let's call the clustering C. Remember that the empirical clustering is what? It's 1 over n but this is a sample quantity. It's actually estimating a population quantity, namely just the expected value of this thing. So if I gave you the true distribution, in principle you could find, and again ignoring computational problems, you could find a set of clusters which minimizes this population quantity. If there was only one cluster, this would just be defining the mean. So this is a very natural thing to be looking at. And when we're doing the algorithm, we're using the empirical version. And a natural question that arises then is, if I minimize the empirical version, which is what we do in practice, how close do I come to this? How close am I coming at least to the population quantity that is supposed to be minimized? And this is theorem 12. And the answer is this. If I look at the true risk, this is a lot like, when you do classification risk, and we find, say, a linear separator. And now if I ask, what is the true risk, not the training error, but the true risk of that classifier, how close does it come to the risk of the best linear classifier? This is an analogous kind of a theorem. If I take the true risk of the clustering that I get from the data, so I find C hat to minimize this. This is what you do when you do K-means clustering. Now imagine if I can compute the true risk. I'm hoping it would be close to this. This is random now because there's a C hat here. And in fact, the mean of that minus, and I'm going to call it C star. Let C star be the minimizer of this. So if an oracle knew the true distribution, the oracle would minimize this. What we'd like is to say that this is close to this. And the theorem is that up to a constant, what you get is K d plus 1 log n over n. Which, let's take a look at that. So as K gets bigger, the bound gets worse. That kind of makes sense, right? If you're trying to find a lot of clusters, it's going to be harder to do. A little bit more disturbing is the dimension here. That's going to suggest that it's harder to do in high dimensions. However, interestingly, there's another theorem that was proved just a few years ago, which is later in notes I'm just going to tell it to you, which is another bound. So we can actually take the minimum of these two bounds, which is K. This is proved. So this is proved using BC theory, and this is proved using something called Rademacher theory, which we'll talk about all these things later, of course. And this is an interesting case where the two proof methods lead to very different bounds. Which one's better? Well, let's look. Root K certainly seems better than K, right? So in terms of cluster number, this is a better bound. But the right-hand side has the amazing property that it's dimension-free. So in some cases, this is smaller, and in some cases, this is smaller. So it's the minimum of those. So in high dimensions, you want to think of it as this bound, and in low dimensions, you probably want to think of it as this bound. And there is some lower bound theory, some minimax theory for all of this, which which is really messy, but I stated the theorem 13. Which says that the best you can do is k 1 minus 4 over d over n. So there's kind of a gap between the upper bound and lower bound. But at least at the time I wrote these notes, this was the best known lower bound. So I think the right thing to do is maybe not do the proof today, because it'll take up the rest of the class. But I think when we do VC theory, we can do it as an application of VC theory, because it really is simple. Once you know the VC stuff, it's actually a fairly simple proof. At least this, actually they're both very simple. I have to tell you, both this proof and this proof are quite straightforward. So the good news about k-means clustering is we do know a lot now about the theoretical properties of it. And we do have ways of picking the starting values. The bad news is I'm not sure we have a really good way to pick k, and it's not clear that the clusters that come out are always meaningful clusters. So there's pros and cons to all these clustering methods. An advantage of this, though, over the density clustering is in high dimensions. This is still easy to do, but the density stuff I talked about gets pretty hard to do in high dimensions. So on grounds of simplicity, k-means has a lot going for it. Okay, any questions about?
If k increases, shouldn't the difference decrease?
The true risk, so there's two things going on here. The population risk, if I drew it, will decrease with k. But don't forget, you're estimating the clusters from the data, and it gets harder and harder to estimate more and more parameters. So getting close to the true risk just gets more and more difficult. Well, yeah, sort of, but nothing that you could actually turn into something which would, as far as I know, give you a way to now pick k. Because it is, you're right, it's getting harder and harder to track the decrease of the true risk. Yeah.
So isn't that the true risk decreases more rapidly than our ability to estimate the true case, the true centroids with height?
Sorry, what was the question?
So basically, you said that there's the true risk that we are unable to estimate. With the high k, we actually have some very nice hidden centroids that we are unable to estimate that way.
Yeah, I mean,
that's the reason.
they're both going down. So the true risk still decreases, and the empirical risk always goes down. As you add another cluster center, it's going to decrease. It's just that how well you track it starts to deteriorate. Oh, yeah.
I didn't understand what claims of stability that was. Is it that, like, if the clusters were good, then it would be stable?
And
or-
conversely.
And conversely.
It's more important the other way around. That people were hoping that if I chose k so I got stable clustering, I picked a good k.
Because the thing, the former sounds true, the latter false, right?
Well, but the hope was that it was true. That if the clusters were stable, you have a good k, was the hope, right? Because that gives you a methodology to see the
But
k.
isn't there a way, still a way of figuring out that it's,
Oh, no, but those examples show you examples where you have the right k and it's still unstable. It's false in both directions.
it's closer.
Yeah, yeah. Which doesn't imply that somebody might not think of a different way of measuring stability that might be good. But you have to be careful. I mean, just to give you an idea of why it might be complicated, think of the two extreme cases. Suppose I pick k equals to 1. That's going to be stable. It's not going to change much. You're just taking the mean. So no matter what the data, even if you have 5 clusters, finding the mean is a pretty stable operation. So that's going to come out as stable. Similarly, if I take k equals to n, each point is its own cluster. And so in some sense, that's also stable because you're just going to get n jiggled clusters when you're in they can't move very much.
So you have cases where it's good but not, sorry, stable but not good,
Right.
or not good but not stable.
Right, that's true. That's only in one direction.
Yeah.
That's correct. All right, so let's now talk about problem is you can have a whole course on clustering. You don't want to do that. I'm trying to decide what's the last topic in the last 10 minutes. I'm not sure there's enough time to start spectral clustering now. Hierarchical clustering, and I'm dithering away time as I'm trying to do this. Well, I'll tell you, let's quickly do hierarchical clustering. That's another one where I think we did this in 701. And I want to mention it though because it's another example of a algorithm without a theory in the sense that, as far as I know, all the results are negative about it. But it is, but having said that, it's very easy to do and very easy to visualize. So do you remember how it works? I take a bunch of data points. And I start by clustering the two closest things. So if I make it schematically look like this, here's the data, and I've just joined these two together. Now I iterate, and I always look for every pair of clusters and find the two closest clusters and join them. Now you have to say what's the definition of a distance between clusters, and there isn't one answer. There's what's called single linkage clustering, average linkage clustering, and I forget the name of the other one, where you look at, and these are written out here on page 24. You can take the distance between two clusters to be the minimum, the two closest points, or the average distance between all their points, or the farthest, which is called complete linkage. Probably single linkage is, I would say, the most common one. So given two clusters, I take all the points and find the two closest ones, and that's the distance between the clusters. And now I iterate this algorithm. So maybe the closest one is this to this, so I join those together, and maybe that becomes here, and then maybe I join these, you know, and you keep going, and eventually everything ends up joined into one cluster. So I'm sure you've seen these things are called dendrograms. Again, we did it in 701. The command in R is hclust. And then a typical thing to do is maybe cut it somewhere, and that will give you some definite set of clusters. Or you look at the whole dendrogram. So this is, the advantage is it's easy to visualize, it's easy to do. It's a greedy algorithm, so it's easy to program. You can do this in high dimensions. There is a question about what is it actually estimating? And there was a period of time when people thought this was doing density clustering. Remember we talked about density clustering on Wednesday? We were finding high density regions of the density. And there was a period of time when people thought single linkage clustering was actually approximating these clusters. And then in, I think it was in 1981, those hopes were dashed. Yeah. This is on page 25. Cardigan basically has a theorem which shows that single linkage clustering is inconsistent. It doesn't consistently estimate the high density regions. The reason why that's true is because if you think about it, this is a lot like doing density estimation with a really small bandwidth. I mean, you're always finding the closest guy and merging it together. And it turns out that's very similar to doing density estimation with a very, very small bandwidth. But we know to get consistent density estimation, you have to let the bandwidth decrease at a very special rate. And single linkage clustering doesn't quite do that. In fact, based on that idea, Sanjoy Das Gupta has a recent paper, 2010, where he modifies the single image clustering algorithm to use k nearest neighbors instead of just the nearest guy. And if you choose k just right, you do get out a dendrogram which is consistent. So there are modifications to hierarchical clustering. This is one of the best ones I know that actually gives you consistent clustering, consistent in some sense that there's some population notion of clustering and you are consistently estimating as you get more and more data. So I'm wondering, I think the plan should be the following, because I think we should talk about spectral clustering a little bit. But I do want to keep us on track, especially now that I've got you all so excited about Wednesday lecture that you can't wait, right? This sounds so exciting. And so I think the right way to do this is we'll come back to spectral methods later on. This is number 4, method number 4, section number 4 in your notes. It's a different way that's very similar to density clustering. And we'll talk about that later. The summary of what we've done so far really is I wanted you to see density clustering, which we did in a little bit more detail because I think it's a little bit more theoretically well justified. Then there's mixtures and k-means. Those are probably the two of the most common methods. And as we've seen, there is some theory for k-means clustering, but how to choose k and whether it gets good clusterings are still somewhat problematic. But it is nice because it can be used pretty easily in high dimensions. And then there's this spectral clustering, which I think we'll fit that in another part of the course, so that on Wednesday, again, we're going to talk about foundations and about Bayesian inference. And so there are 2 sets of notes. You don't need to bring both of them on Wednesday because we're going to start with the first one. And a lot of what's in there you already know. We're going to talk mainly about the foundational issues because I think the mechanical issues you already are familiar with, although that's another thing I guess I should check to make sure of. If we need to review the mechanics of Bayes, then we can do that as well. We did do some Bayes in 701,